So the end of the 19th, beginning of the 20th century, we started to discover what's going on with nuclei in more detail, and Marie Curie was very instrumental in helping us understand what's happening. And so, she and other scientists discovered that some nuclei are unstable, and those nuclei emit particles and become different nuclei. And this is radioactivity. And as Marie Curie worked through these experiments, she was very instrumental in the discovery of much in radiation and better understanding the elements and what's happening in terms of the change of nuclei as they go from become one or different kinds of elements through the decay cycle. So in a nuclear decay, they're random and spontaneous, and where an unstable nucleus ejects a particle and changes to another nucleus. And so there's alpha decay, which we'll talk about. There's beta decay. There's two types, beta minus and beta positron decay. And we'll also be talking about fission, where a nucleus splits into two fragments, and fusion, where nuclei combine together to form another nucleus. The other type of decay, it's not ejecting a particle, but it's also ejecting gamma ray, and that's another type of decay we'll talk about. So with alpha decay, they found that these were positive emissions, where a nuclei of helium, 2 positive 2e, 2 protons, 2 neutrons, was shot out from a nucleus. And those particles came into contact with electrons, and by analyzing the spectrum, they found that these were alpha particles. And so using the quantum physics that we've learned, to be able to see that these were helium nuclei. So here's a visualization of that. We have a plutonium nuclei that ejects a alpha particle, and as it does, becomes uranium. And so this is how we would write that out. We have the nucleon number here, we have the proton number here, and afterwards we have a helium nuclei, which is 2 protons, 2 neutrons, and then we have what's left, which is the uranium nucleus, which you can see here. And so alpha decay occurs only with very heavy elements. You can see here with plutonium 239, it's a lot of nucleons there, and yeah, and we can see the charge here is positive 2. We have the charge down here. So the discovery of the alpha particle, and Rutherford and Royds in 1909 collected gas samples, alpha particles produced, or collected gas alpha particles produced, and then looked at the light produced when it came in contact with electrons, and yeah, discovered it was helium atom that was actually shooting out, well, helium nuclei, and then when coming in contact with electrons, they become neutral atoms, and then as those atoms get excited, they can electrons will go to the outer energy levels, drop down, and shoot out photons of light. And so we have very, very specific photons of light that are produced. Now with weak nuclear force, we have the changes in the W and Z bosons in the nucleus. There's 2 types of beta decay, and one type is where emissions are electrons that shoot out. And so experiments similar to J.J. Thomson's electron mass experiments, they were able to discover this type of decay and understand what's happening. And one of the things that's interesting here is the ratio of the charge to mass was actually lower. And so this was an early proof of the theory of relativity, Einstein's theory of relativity, where you have that discrepancy in what's going on with mass, which we'll get into great detail. A mass of an object increases as the speed becomes comparable to the speed of light, and this was starting to be seen here with these beta particles. So a neutron decays into a proton in a nucleus, and an electron and an antineutrino are released. And so if we have beta decay, that neutron itself becomes a proton. And again, this will happen in a nucleus if there's too many neutrons, and that neutron will become a proton. So what we see here is we have now a proton, same atomic mass here that we see. But now we have +1 charge, and so we know with conservation of charge, if we started with 0 charge, we should finish with 0 charge. So what happens is that proton, or the neutron, becomes a proton and then shoots out an electron, and therefore with that electron plus the proton, we still have neutral charge. If we added them up, we'd still get 0. So we start with 0, we finish with 0. And then we finish with an antineutrino. An antineutrino shoots out, and the way that you can remember, hopefully, an antineutrino, there's a bar on top of the V representing antineutrino. And so as the particle shoots out, an antineutrino must be released as well. And the reason for that antineutrino is very, very important. And Enrico Fermi, is part of that, and we'll talk about that too. In beta minus decay, here's an example here where we have a carbon nucleus, carbon nucleus, carbon 14 in this case. And what happens is this has too many neutrons for as many protons as we have. So one of the neutrons becomes a proton. And when that happens, we go from a +6 charge to +7 charge. And then again, for conservation of charge, an electron must shoot out. And as an electron shoots out, an antineutrino also shoots out. And so the arrow represents the transition here. We go from this carbon atom, carbon 14, to this nitrogen atom, and then we have that there. So again, this is called beta minus decay, where there's too many neutrons for the protons there. Neutron converts into a proton, and the antineutrino is released. So why was another particle needed? Well, this was first postulated in 1930 by Wolfgang Pauli to preserve conservation of energy, conservation of momentum, and conservation of angular momentum in beta decay. There was a major issue here as we had a nucleus and an electron, shoots out. Conservation of momentum, right? We have an issue here with the nucleus itself. We know that if we had a cannon, we have a cannonball that shoots out to the right. The cannon's got to go to the left, and so it turned out that it did not look like energy was conserved, momentum was conserved, angular momentum was conserved. So they were almost questioning that. Okay, maybe conservation of energy, momentum, angular momentum are relevant here, so they proposed that there was this other particle that would help show the conservation, and it wasn't until later that they actually discovered this particle. Right, so in beta decay, a proton turns itself into a neutron and then releases a positron, and we can write out the full equation here. We start with a proton. So we're starting with a +1 or positive E charge, right? So we should finish with that. What happens is when that proton turns into a neutron, it shoots out a positron. It's a positively charged electron, and that's the antiparticle of the electron.
Yes.
Also shoots out a neutrino. So remember before where we had the electron shoot out with an antineutrino that shoots out with the neutrino. And so we can write out this equation here. We have helium turning into hydrogen, and one of the protons of the helium turns into a neutron, so a proton into a neutron, and therefore shoots out a positron and a neutrino. And again, a neutrino is released, looking at conservation of energy and momentum. Okay, so one of the things that we want to picture with the nucleus is the fact that with the nucleus, it itself, if there's too many protons and neutrons, we kind of anthropomorphize it. It's going to want to shoot out an alpha particle, and this alpha particle is 2 protons, 2 neutrons, and typically what happens then, when it decays, the nucleus itself is in an excited state, and so what it needs to do is shoot out a photon, and it'll be at a lower state, and then it can shoot out another photon and go down to the ground state, and so over that progression, shoot out an alpha particle, and then you have the 2 gamma decays there.